Hello and welcome back. Today we're going to cover the Chapter 1, Part 3 lecture on the nature of science. You should use the information in this lecture to complete the Chapter 1, Part 3 guided notes and pre-class quiz. All of this should be completed before you come to class. We have three major learning objectives for this lecture. First of all, we're going to go over science and define it, describe what it is and what it isn't. Second, we're going to go over 6 basic scientific principles that we use to define what science is. This will include a review of the scientific method. And then finally, we're going to discuss scientific theories, laws, and models, different types of scientific ideas. So first, let's just start with a very simple definition of science. Science is the systematic study of the observable world. Science is a way of thinking, and it's a way of looking at the world that is very logical and systematic. So it depends very much on reason, and there's a sort of series of steps you go through when you think about a scientific problem. And this way of thinking is very organized. Science also represents a body of knowledge. You're going to begin learning this body of knowledge in this class. And the knowledge that we get from scientific pursuits are based on experimentation and observation. The knowledge that we gain from science, we say, is objective for that reason. Now, why do we perform science? Why think scientifically? Well, as with many schools of thought, the main purpose of science is to try and make sense of our environment. We're trying to figure out what is true and what is not true and make that all make sense. So science can represent many things, but at its heart, its defining characteristic is that science is concerned only with those things that can be observed, measured, quantified, or qualified, that are confirmable and also falsifiable, and we'll talk more about what that means in a moment. For instance, if you look at this little boy observing this butterfly, he can make quantifiable observations by making measurements, by counting the scales, by counting the legs. He can also make qualified observations by looking at the color, the intensity. He can make a description of that organism. It's not what he feels about the butterfly or what he believes about the butterfly, it's what he can observe. So in science, our conclusions are based upon experimentation, data, and replication. That means that we can perform an experiment more than one time and get similar or the same results. Now really, we're all just trying to figure out what's true about the universe. Science is one approach to trying to figure that out, but there are many other schools of thought, and some of these include non-science, and religion does fall under this category. So what's the difference? Well, whereas science depends on things that are observable, measurable, and quantifiable, non-scientific schools of thought do not depend on evidence. Non-scientific schools of thought depend instead on this word, belief. Now think about what belief means. A belief is an idea you have, something you think you know, and you will think that you know this thing regardless of whether you have any evidence or not. And in fact, think about it. Oftentimes people will cling to their beliefs even harder when evidence is presented that contradicts it. So belief does not require proof. It does not require evidence. Now that's fine. Schools of thought such as religion have a very important place in human culture and in human psychology, so I'm certainly not saying they're bad. But they are a different way of thinking, and they are not scientific ways of thinking. So here we have a fun little cartoon illustrating the difference between science and non-scientific schools of thought. We have these two scientists and they're discussing their research. And the one, of course, is saying, well, I can't actually verify the radioactive decay, but I know it's there because I feel it deep inside me. Okay? The feeling it deep inside himself, that's a belief. Being able to measure it and quantify it, that's science. So in scientific circles, this kind of a claim just doesn't cut it, just doesn't fly. If you can't measure it, then it may as well not exist. And if you want to prove that it's there, you have to keep searching for a way to actually measure it. In addition to being based on observation, scientific claims must be falsifiable or able to be disproved under particular conditions. In science, a hypothesis asserts that there is a relationship between two things. That if A is true, for instance, then we will observe a certain change in B. For example, I might assert that bleach stains all clothing. So if I pour some bleach on some clothing, I should see it bleach out or stain or turn white. However, in order for this claim to be considered scientific, there should be a set of conditions by which we can disprove this hypothesis. In this example, we might say that if we pour bleach onto some clothing and it does not stain, it does not turn white, then that claim must not be universally true. We can both prove this hypothesis and disprove it under certain conditions. Now, not all claims meet this criteria. In the cartoon, for example, the guy is claiming that purple walruses can be found on Pluto. Now, we have no way of either proving nor disproving this claim. So that claim is not falsifiable. There's no way to disprove it. A lack of evidence does not constitute evidence in science. So that claim is not considered scientific and should be approached with some skepticism. Another rather insidious phenomenon that we see today is something called pseudoscience. And we are just saturated with pseudoscience in today's culture, largely because of the advent of the internet. The internet allows us to share information really quickly, but it also allows us to disseminate misinformation practically at the speed of light. So there's a lot of sciencey sounding stuff out there that's not true. So pseudoscience is the use of scientific language, imagery, etc., to sell you on an idea or product. Now that information, in quotes, may or may not be true, it may or may not be supported by evidence, but it will always sound kind of plausible because there's usually a little grain of truth in there somewhere, but not the entire truth. Remember that the main purpose of this sort of pseudoscience is to sell you something. So the people who are selling these things don't care if they confuse you or mislead you. They just want you to buy into the idea or buy the product. This ad shows one of my very favorite examples of pseudoscience. Back in the day when they discovered that cigarettes are in fact bad for you, which we know is true, this company put out a series of ads, and this series of ads shows doctors smoking. And this one's my very favorite because this guy in the ad is a scientist. So you can see that he's looking through a microscope. It's probably 2 a.m. and he's doing a lot of science, working really hard, and he's just chain smoking these Chesterfields. So why would this convince you to buy cigarettes? Well, if doctors smoke, if scientists smoke, and they're really smart, then it must be okay to smoke cigarettes, right? So it's misleading, even in the imagery that's used. We're going to look at some examples of pseudoscience in class, but I would encourage you to learn to recognize it and to be very skeptical of this sort of thing, to really do your research before you buy into products or ideas, because there's just a ton of this out there. Now, an important skill for you as budding scientists and also as consumers is something known as critical thinking. Critical thinking means that you are able to evaluate the quality of information that you're presented with. So I want you to practice that in this your turn, and you'll find this your turn on the guided notes as well. Here we have a really interesting product. There are many beauty products out there that include this ingredient called snail gel, and essentially it's snail mucus from a very particular kind of snail. And it's supposed to moisturize the skin and kind of youthify the skin. Now, before you buy this product, I want you to ask some questions about it. So I want you to come up with several questions, things you want to know about this product that you would answer before you go out and buy it and put it on your skin. So brainstorm that, write down your answers, and then bring them to class and we'll discuss them. Next, we're going to discuss 6 scientific principles that kind of help us define what science is, and it helps tell us what science is not as well. The first one we've already gone over. It's the idea that science is concerned only with those things that can be observed. The second scientific principle talks about the limitations of science, and this is something that people aren't always comfortable with. We really want science to be able to answer any kind of question that we have in our heads, and it really just can't do that. So what kinds of things can't science be used to explain? Well, things like social trends, things that people find popular, human desires, human preferences. It also can't be used to describe morality. Okay, we apply morality to science. So science in its purest form is neither good nor bad. It just depends on how we apply it. Think about how many sci-fi movies you've seen that discuss this very question. Okay, we can create these self-intelligent robots and they can do these wonderful things for us. But what are the moral implications on that? You know, if the robots turn on you and try to kill humanity, that kind of thing, we question that all the time. Science also can't be used to work on things that can't be observed or measured. We discussed that already. Or things that can't be directly tested. So science is actually pretty limited in what it can do. You'll find this your turn on your guided notes. And what I'd like you to do here is to examine these different questions and really think about them and tell me which ones you think could be answered scientifically and which ones really can't be answered scientifically. As you think about each one, think about, do I have a way to test or prove this? Is there a way to falsify this? Can I disprove it under the right conditions? Okay, bring those to class and we will discuss them. Okay, scientific principle number 3 is that science is honest. That means that if you're reading a scientific paper and looking at some data, that data has been presented honestly and truthfully, that those numbers reflect reality and haven't been fudged and haven't been presented with bias. Now that's a tricky one. Even though science is honest, scientists are not always honest. They're human beings, they are under certain pressures. And so we have to have systems in place to kind of keep us honest in this regard. So one of the systems that's in place that's helpful for this is something called peer review. Peer review means that if you publish a paper, the world's leading experts in that topic are then going to start looking at that paper. They're going to look at your experiment, your hypothesis. They're going to examine your data and make sure that it's honest. If it's not, they may not publish it. And if it gets published and they find out that it was dishonest, it can absolutely ruin careers and lose funding. So there's a lot of pressure to be honest in science, and it's absolutely a good thing. Scientific principle number 4 is that science is tentative. What we mean by that is that if we think we know something in science and new evidence comes out that contradicts it, we are obligated to take a look at that new evidence and work it into current theories and reject ideas that no longer make sense. So science is constantly changing, and that's a good thing. That means it doesn't get stuck. It doesn't become rote dogma that's not going to change and evolve as we learn new things. Because the point of science is to learn new things. Scientific principle number 5. When we answer a question in science, we use reasoning and a specific set of steps to answer that question. And we call these steps the scientific method. We'll be going over the steps of the scientific method in detail in just a minute. Scientific principle number 6 is that science is a process of elimination. So we like to think of science as being this process where we try to prove things and we feel good about ourselves. But really, failure is a very important part of the scientific process. Let me give you an example. Let's say that you go out and you try to get in the car and the car won't start, or it's running rough, and you need an explanation for what's going on. Well, there are several possible explanations, and you're going to go through them one at a time. Let's say that first you theorize that the battery's dead. Okay, that's fine. You test the battery's fine. Well, you can mark that off your list. Okay, that hypothesis has been disproven. Next, maybe you think about the gas. Maybe it's out of gas. You test that. Nope, it turns out there's gas in the engine. That's fine. You can eliminate that as a possible explanation. And then let's say you open the hood and you in fact have an engine snake, as shown in this picture here. Okay. Engine snake is the actual explanation, the one that's true, but you couldn't really arrive at that until you started eliminating some of the other possible explanations. So science is a process of elimination. Now that we've discussed the 6 scientific principles, I want you to do your next year turn. In this year turn, you're going to use Now that we've discussed the 6 scientific principles, you can perform this year turn. This year term contains a concept map to help you summarize the 6 scientific principles, and it's very simple. On this building we have 6 pillars and we have 6 ideas. So what I'd like you to do is to summarize the 6 principles on these pillars. So for instance, one of our ideas is that science is honest. So you can write honest on one of these pillars. I can't write sideways with this pen. Okay? You can write the other 5 on these pillars. You'll want to summarize these ideas in 1 or 2 words so that you can fit them on these pillars. Okay? But this is going to help you remember what the 6 scientific principles are for test time. Now, when we ask a question in science, there are a series of steps that we need to go through so that it's systematic and logical. And we call this the scientific method. There are many different treatments of the scientific method, but these are the 5 basic steps we're going to use: observation, hypothesis, experiment, data, and analysis. So let's go through each step. Our first step in the scientific method is very simply making an observation. Hey, that's a neat thing that I saw and I'm curious about that. I wonder, does this work, or how does this work? Observations generally lead to further questions and to making predictions. So let's say, for instance, that you're curious about the effects of fertilizer on a plant. So maybe what you want to do is get a nice little house plant like this, that's a plant, and put some fertilizer on it and see what happens. Your observation is that fertilizers might make plants grow faster. The second step of the scientific method, and actually the most important step, is called the hypothesis. A hypothesis is a tentative explanation for why your observation is occurring. It's an educated guess. And this guess actually links together 2 of the variables, 2 of the things you observed. There is a proper format for writing a hypothesis, and I would like you to use this format in this class. And essentially you say, well, if A is true, then B must occur because of some reason. So if I see A happening, or if I change A, then B is going to happen. And because would be why I think that happens. A hypothesis is a claim that there is a relationship between 2 variables, 2 things in the situation. And these variables are known as the independent variable and the dependent variable. Let me give you an example to explain what these things are. The independent variable is the variable being tested. So let's say you're testing that fertilizer thing on your plant. So the effect of fertilizer is what you want to test. That's your independent variable. Okay? Now the dependent variable is the thing that will change in response, or the thing you're going to measure. So let's say that in this experiment you're going to measure the height of the plant. That is going to be your dependent variable. Now you can use these two variables to make your hypothesis. You can say, if I put fertilizer on the plant, then it will grow faster. And you could add a because, something about nitrates or nutrients in plants, if you wanted to add a because. But a good hypothesis says, if I change the independent variable, then the dependent variable will change in a certain way because some reason. So there's a relationship between these two variables. After you've written your hypothesis, you can perform an experiment. An experiment is the actual testing that goes on. And the design of an experiment is really important. Good experiments minimize variables. Now, what do I mean by a variable? Well, a variable is any factor that could affect the outcome of your experiment. So you're testing your independent and your dependent variables, but there are always going to be others involved too. For instance, with a plant experiment, you can have all of these other variables going on. You can have predators such as slugs nibbling on your plant, the wind, the amount of sunlight, the temperature and the pressure, the amount of water that you're giving it, the type of fertilizer you're giving it. All of these things, even the soil, can affect how that plant grows. In order to minimize these variables, you want to keep these factors as constant as possible. And if you can't control the variable, then you really need to record that variable. You need to keep measurements of it and see how it changes. That way you can kind of account for it in the results of your experiment. So good experiments try to minimize variables. An excellent way to help minimize variables is to run something known as a controlled experiment. A controlled experiment involves replications of your original experiment. But in these replications and these other experiments, the independent variable has not been changed. So they represent kind of the natural or normal state before you started changing stuff. Controlled experiments are important because this control group gives you something to compare your experiment to. It helps validate that relationship that you are claiming exists between your independent and dependent variables. Let me give you an example. Here we have an example of a controlled experiment. Let's say you're doing your little test with the plants and the fertilizer. You have a plant here, you've been putting fertilizer on it, and you've been measuring the growth of the plant over time. Now your plant is growing, and that's awesome, it looks really good, but you can't really say that the growth is due to the fertilizer if you don't have anything to compare it to, because you don't know how the plant was going to react normally without the fertilizer. So what you might do is include a control. So here's our experimental group, right here. Here's our control group. So here we have a plant that's the same type, maybe the same size, same health levels, and you are treating it with just water instead of water and fertilizer. Now the variables between these two plants needs to be the same. So the atmospheric pressure, the amount of sunlight, the exposure to predators, all of that stuff needs to be the same between these two groups so you can make an accurate comparison. The only thing that you want to differ between these two groups is the fact that this one gets fertilizer and the fact that this one doesn't. That way, if the fertilizer plant grows faster than the water-only plant, you can say that it's the fertilizer causing the increased growth. Now, this particular type of control is known as a positive control. It's known to produce certain results, and positive controls usually sort of represent the natural conditions before you started changing things. Another type of control that is sometimes used is known as a negative control. In a negative control situation, typically something is removed so that you get the opposite results to the positive control. Negative controls are not always necessary, it just depends on the experiment that you want to do. But in this case, if we wanted to add a negative control, maybe we could have a plant that we gave no water to. Maybe we suspect that the water is making it grow more than the fertilizer, so we'll give this guy no water and see what happens, and there's my prediction about what it will probably look like. That's a negative control. As you perform your experiment, you're going to be collecting data. And data can be presented in a number of different ways. It can be quantifiable or qualifiable. It can be presented in tables or charts or pie graphs. It can be mathematical proofs. Here we have graphs, different kinds of graphs. It can be photographic evidence. It can be really nice drawings or even really good descriptions of what you see going on. In this next step, you're going to analyze your data and you're going to draw conclusions about what you're seeing. This is the point at which you are going to relate your hypothesis back to your data. And you're going to say, okay, does my data support my hypothesis or not? Does it make logical sense? Was I able to repeat the experiment more than one time and get the same results? Is my data reliable? This is the point at which you're going to decide whether to accept or reject your hypothesis. We really say accept and reject in science rather than prove and disprove, because prove makes it sound like you're at the end of the process, and really you're not. Now remember that rejecting a hypothesis is not a bad thing, because science is a process of elimination. But this is the point at which you will make that determination. You might decide that you need to go back and tweak your hypothesis or tweak your experiment and keep going, or you might decide that you've arrived at the answer you were looking for. Here's the data I collected from our little plant experiment. Kept track of the height over a month, and you can see the growth when we began, without fertilizer and with, and at the end. And very simply, you can see that the plant with fertilizer grew faster than the plant without fertilizer. So from this, we might conclude that fertilizer increases plant growth. We might accept our hypothesis. Again, we might want to go back and tweak our experiment and change it a little and try it again. Maybe more fertilizer makes it grow even faster. You might want to test that. Okay, but that's the analysis and conclusion part of the process. Now in this class, usually you'll just run an experiment once, and that's sufficient for our needs. But in real science, at this point in the method, we're going to start over again. Again, we're going to tweak that hypothesis, tweak the experiment, and try to replicate our results and do these experiments over and over again. If we were doing a plant fertilizer experiment, we wouldn't just have 2 or 3 plants. We'd want hundreds of plants so that we could really collect a lot of data and make sure that variables like genetic variation among the plants wasn't affecting how they grow. So this is just the beginning of the process all over again. Time for another year turn. You'll find this year turn in the guided notes. In this year turn, what I want you to do is think about what might happen if you go out in the parking lot and your car won't start. You can actually use the scientific method to try and figure out what's wrong with your car. And so what I want you to do is brainstorm that and work through the steps. Your observation is that your car won't start. What possible hypotheses could you come up with for why the car won't start? What experiments would you do to test this? What data would you collect? And what conclusion would you draw depending on what data you were able to collect? Okay, write this out and bring it to class with you. Now, once all of these great experiments have been done and all of this wonderful data has been collected and analyzed, We can use this information to form certain kinds of scientific ideas, including theories and laws. For this portion of the lecture, I want you to watch this video and use the information in the video to answer the Your Turn questions in the guided notes. It's going to give you a nice, thorough explanation of these different types of scientific ideas. The link for the video is posted in the green comment on the left-hand side of the page and on the next slide.
We need to get something straight. Evolution by natural selection is a theory. So is climate change. But people keep saying that like it's a bad thing. I get it. I understand your frustration. We're all searching for ultimate #truth, and complex, challenging ideas don't always fit nice and neatly in our brains. But what is truth? Are there different levels of truth? Are some truths truthier than others? Well, I don't know, but I do know this. Science is the absolute best tool we have for understanding how the universe works, and theory is not a four-letter word. If we're going to trust science together, the least we can do is speak the same language. Words like fact, theory, hypothesis, and law mean something totally different to a scientist than the way they're used in everyday speech. So let's get them straight. Facts are really just observations about the world around us. And we observe things every day, like that it's bright outside when I look out the window. And we often develop explanations for those observations, like, okay, the sun is probably up. Congrats! We just developed a hypothesis. But a hypothesis isn't something you prove. It's something you test. So, let's walk outside. It's bright, the sun is up, hypothesis confirmed. Way to go! We did a science. We often come up with multiple hypotheses to explain an observation. We just eliminate the ones that are wrong. What's left over is not a theory or a law or an ultimate truth. It's just a possible explanation for something, one that can lead us to new hypotheses, which may agree or disagree with the original one. It's a never-ending story, only without the big fluffy dragons.
That's so good.
When enough hypotheses have gotten the old scientific check mark, we can pile these all up and turn them into something greater, a theory. A theory is the way we know something works, based on the evidence we've collected and all the hypotheses that we've successfully put to the test. The best thing about a theory is that we can use it to make predictions, and not just about the way things are, but how they will be. You may have heard someone say something like, I have a theory about why cats purr. I think it's because they're actually tiny robots, and those are their gears. Well, that's not a theory. That's actually a hypothesis. It's something that could be tested, but don't try this at home. This cycle, taking facts and observations, thinking up possible explanations, testing those explanations, and then making predictions based upon them, that's what this whole science thing is about. Being a theory isn't a bad thing. It means that idea got the gold star, the blue ribbon, a big shiny trophy that says, countless experiments have shown that I'm sufficient to explain all the observations that I encompass. Now, to see if you got this down, let's look at some examples. Fact, people get sick. I think we can all accept that. Hypothesis, people get sick because something gets in their body and starts doing bad things. Test each hypothesis, throw out the bad ones, and we're left with a framework that lets us understand why we get sick and make predictions. The germ theory of disease. Okay, let's try another. Evolution is a fact. We know that it happens, no doubt. But how does it happen? Evolution by natural selection is a theory. We've come up with thousands and thousands of hypotheses about it, tested them, thrown out the bad ones, and we've developed a pretty darn good framework for predicting how living things change over time. So yeah, it's a theory. Stop saying it like a bad thing. Calling it a theory means it's passed the toughest tests that we can throw at it. And evolution has been tested maybe more than any other theory we know of. We should really call it the theory of the fact of evolution. What about something as fundamental as gravity? Is that a theory or is it a law? In science, a law is a detailed description, usually using math, of how something happens, like the movement of gas molecules related to temperature, or how mass and energy are always conserved. But a law doesn't tell us why something happens. Gravity, as it turns out, is a law and a theory. Newton's law of universal gravitation describes precisely how two objects will attract each other based on their masses and the distance between them, and gives us a nice formula we can use to figure it out. Textbook law. But Newton's equation doesn't describe what is happening or why. To do that, we need a theory of gravity. Fact: if I drop this, it'll fall. Law: I can mathematically describe how fast that apple and the earth will accelerate toward one another based on their masses and distance. But why is it happening? Hypothesis: there's a force pulling on the apple, or maybe there's something about the universe and the way it's structured that makes massive things fall toward one another. Or maybe the apple is like magnetically attracted to Earth or something. Eliminate the bad ones and we're left with a theory. And thanks to Einstein, we've got a theory of gravity called general relativity. But once scientists stumbled upon quantum mechanics, they began to realize that Einstein's relativity didn't account for what was happening on the very smallest gravitational scales in the universe. General relativity is still great at describing the universe at the scale that we interact with it. But even the theory of gravity is incomplete. Does that mean we throw it out because it can't explain everything? No. I mean, if you get a flat tire on your car, do you get a new car? If you change the tire, is your car a different car all of a sudden? All of these fit together to make the scientific machine. We're constantly adding and taking away parts, but it keeps on running just fine. It just means we've got more work to do to make Einstein's theory even more right. Science is never done. It's always changing, and this bothers some people. How can we trust it? How can something be strong and robust if it could be different tomorrow? The goal of science is to devise frameworks that describe how things work, to truly understand why things are the way they are right now, so that we can know how things will be in the future. And if we can learn to trust science in all of its fuzziness and incompleteness, I predict that future is going to be very bright. I like that theory. Stay curious. Otters are cute, curious, playful, cute, intelligent, fluffy, and did I mention cute? But they're more than just adorable animals. Otters are the cornerstone of one very important ecosystem.
Hooray! You're almost done. You're almost ready for class. At this point, you should make sure that your notes are thoroughly filled out, and then you should go and take the Chapter 1, Part 3 pre-class quiz. This quiz is posted on Blackboard. It uses the information in your notes, and it is due 30 minutes before class starts. So go and get it done. See you in class.